Well, hello there, math fans. It's been a while since I've done a more fun video. I thought I would do something for Father's Day. This is a problem I've thought about for a long time, and I'm not going to solve it here. I'm just going to present it. I have this idea of presenting problems and hoping that they could be student projects in the future. But here's the story. When we would go to a restaurant, we would get a cup of ice water or Diet Pepsi or something. And so when I was a kid, we would often like to get straws. My dad never got a straw. He was ahead of his time, I guess, because straws now are frowned upon. He would drink off the top. And we would debate, is it colder to drink out of the straw? Heat rises. Or colder to drink off the top? And just one of those goofy conversations, parents and kids have over the years. We also would talk about how if you hold your finger over the top and lift it up, and then hold it over your sibling's head, it could spray. We also did spitballs sometimes over the table. Lots of questions. And so I've started to think about these are the sorts of things that I think could lead to fun little projects for students, get to use a little bit of calculus and see what happens. So I now agree with my dad that I would rather drink off the top. It is colder. I have my thermometer. I measure right off the top, and I measure it off the straw. Now, the only thing about the straw is it's the amount of liquid going in your mouth is coming from the top. But I do think as you suck out of the straw, it's a little warmer. But even a goofy question like this can be turned into some sort of project. And so I did a little bit of an experiment, kind of a heat flow experiment, and I don't have the answers here. And that's why I'm presenting it this way, and I hope it leads to more. I was going to wait to do this video, but since it's Father's Day, I'll do it now. I did this actually several months ago. But here's my little diagram. And my goal here is to think of problems that I don't have answers for and say, here's an avenue for exploration, more of a place for you to see how math is used. And if you do want to watch, I do have another video about how the roots of unity saved my dad's life. So keep asking small questions as you do things. But this is the scenario. And I'm thinking, like, what is the temperature at a given layer as you put ice in there? So I ran the experiment, very informal. As I said, I'm leaving this open-ended. But I occasionally measured the temperature at the bottom and at the top. The top is kind of hard to measure because it tends to measure like the ice that's next to it. Anyways, I did that little experiment, and this is what I got. So the temperature went down, the temperature at the top initially went down, which was interesting, and then went back up. So that got me thinking about the model. After about 5 to 10 minutes, the temperature balanced out. Okay. So the main tool we use in like our regular calculus class, how this relates to a calculus course, is this thing called Newton's law of cooling, where we say the rate at which the temperature is changing, basically like the degrees, whether it's Fahrenheit or Celsius per, let's say, minute, is proportional to the difference between the temperature of the object and its surrounding. Some percentage of the difference in temperature is lost. So I did this for the bottom. I treated the bottom like a typical Newton's law of cooling problem. I kind of toyed around with it. Again, this is me just trying to get a graph that was reasonable, not actually studying the theory. And so I assumed we had a model, an exponential model, which is what we get from Newton's law of cooling. I found the coefficients, as you can see them there, and I made this little graph. So let me share that with you. Make my fat head a little smaller. Ooh, I'm peeking. Hello. Hello. All right, so here we go. This is it. So the green line there is the temperature of the bottom of the glass. And I suspect that's pretty accurate model. That's kind of what Newton's law of cooling looks like. Given the first few measurements, it approaches about 40 degrees Fahrenheit. I then said, assume that the water at the top is is changing proportional to the temperature at the bottom. Now that's probably not an accurate description, but I was trying to get this little bump behavior, which gave this. So I thought that was kind of neat that I got that. And then lastly, I wanted to show I made up a function kind of for what happens after that. It will then approach room temperature. I have a feeling my model there is less accurate. Okay. So there's an avenue for study. Now, that's an example of heat flow. So there's these problems in differential equations where you study the heat flowing through a rod and then like the heat flowing through a wall. These are important in insulation questions. So this maybe isn't as far-fetched of a question, but I leave this for students. It would be cool to do a more thorough experiment with lots of measurements along the way and get real good data for how it moves, see how good Newton's law of cooling is, see how it doesn't work. This is all part of the scientific method. Most language, though, in science like this is stated in terms of rates. So this is a nice another example of this. It's just how do we change the model to answer such questions? How does the ice melt? Maybe we need to get some chemistry people involved for the temperature. If you really want things to work, you want to understand the underlying dynamics, how it works. So there's my question for a project is, how cold is the water once you push the ice in? I think we should drink from the top. So this is a good story for those that are against straws for the environment. It's colder without those straws. So I agree. Let's get rid of those straws. And happy Father's Day to my dad. I think I'm confirming he's right. But his questions and the questions your parents asked, I encourage you to study them and ask me about them and give me ideas related to this in the comments. All right. Thanks for listening.